Welcome to Six Sigma Black Belt, Course 5, Module 2, Hypothesis Testing Terminology. Hypothesis testing is the most important application within statistical work. We seek to use data to make inferences about the performance or behavior of a process. Let's begin by outlining a number of terms and ideas associated with hypothesis testing. The null statement is the statement we accept to be true. It is denoted as H sub 0. An example might be, if one is investigating whether a pesticide will result in different heights of corn stalks. The null hypothesis would assume the heights are the same. This would be a two-tail scenario. Another might be a claim that 8 hours of sleep yields greater average test scores over student test scores from students who only get 6 hours of sleep per night. The null hypothesis would state that test scores for sleep-deprived students is less than or equal to test scores for students who sleep 8 hours a night. This is a one-tail test. Hypothesis testing is a lot like the verdict in a trial. We find people guilty or not guilty. We never proclaim a person is innocent. This is also true of a null hypothesis. We will not accept a null statement, but instead fail to reject a null statement. In hypothesis testing, we seek to find what it is not what it is. This is based on a preponderance of evidence or lack of same. Since null and alternative statements are mutually exclusive, rejecting a null statement means that we must embrace the alternative statement and the reverse. There will be no option beyond these two camps. There are two ways to test a hypothesis. One is to compare the p-value to alpha. We will address this later. The other is to compare a test statistic to a critical statistic. A test statistic calculation is made from sample data. If the magnitude of the test statistic is bigger than the magnitude of the critical statistic, we reject the null. If the magnitude of the test statistic is smaller than the magnitude of the critical statistic, we fail to reject the null. Like any other inference, there is always a possibility of being wrong. We have two classifications of being wrong, called type 1 and type 2 errors. A type 1 error occurs when the null hypothesis is rejected when it is in fact true. The probability of making a type 1 error is called alpha. It is commonly referred to as the producer's risk. A type 2 error occurs when the null hypothesis is not rejected when it should be rejected. This error is called the consumer's risk and is denoted by the symbol beta. The degree of risk, alpha, is normally chosen by the organization. Most organizations select 0.05. A more conservative organization would select 0.01 or 0.005 for alpha. For a fixed sample size, alpha and beta are inversely related. In an ideal world, increasing the sample size can reduce both alpha and beta risks. However, this can be cost prohibitive. We can also make a hypothesis test decision by comparing alpha to p-value. Alpha is the area in the tail of the distribution bounded by the critical statistic. P-value is the area in the tail of the distribution bounded by the test statistic. Note that alpha extends all the way into the tail of the distribution. P-value and alpha partially overlap in the picture shown here. If the p-value area is smaller than the alpha area, we reject the null. If the p-value area is bigger than the alpha area, we fail to reject the null. If a null hypothesis is established to test whether a sample value is smaller or larger than a population value, then the entire alpha risk is placed in one end of the distribution. This constitutes a one-tail test. Note that the null statement always includes equality. The alternative statement tells us which tail we are working in. In other words, where the rejection region is found. These details can be very insightful. In the example above, the rejection region is in the left tail. This implies the test statistic will be negative. If a null hypothesis is established to test whether a sample value is different from a population value, then a two-tailed test is required. The allowable alpha error is generally divided into two equal parts. Again, note that the null statement always includes equality. The alternative statement tells us that we are working in both tails. In other words, there are two rejection regions. Since the alpha is split between each tail, the area in each tail will be half as big. Therefore, the distance from the peak of the distribution bounding half of alpha will be greater. In other words, the critical statistics will be further away from the peak of the curve.